which means, they're not going to match up. At the end, the video recorder may say that I have, 1 hour and 15 minutes, and the sound may say that I have like 5 seconds short of that or something like that. I have tools that can stretch one and match the other one, so we'll see how well that works out. So this is an experiment. What I'll do first is to upload the stuff from the morning class, and I'll do that at the end of today's class before I go away, because I don't have access to the internal hard drive on these computers at home, so I got to do it before I leave here. So let me drag and drop the other files first, and then we'll start today's lecture. And where is it? Oh, right there. This is in my own folder. Data. Alright. So what we'll do today is I will talk about the midterm on Wednesday, because there's one student in my morning class who has not taken the exam yet due to sickness. I think he had pneumonia or something like that, so he was excused. What we'll do today is, we'll talk about functions and modular programming using top-down design. So those are the two focus of today's lecture. The first one is functions. I don't think there's really anything new, on this slide. We have talked about all of these things here, but I just want to be complete and go over the material to make sure that it is all, done here. How many people do not have any exposure to the concept of a subroutine, procedure, or a function? Because those things, they all mean about the same thing. In your previous class, which is cisp 300 or 301, you should be exposed to the concept of a subroutine, a function, or a procedure, depending on how your professor wants to call that, but they're all basically the same concept. So since nobody raised their hand, I'm assuming that we all have some exposure to the concept. So I'm not going to talk about the concept much. I'm just going to focus on the syntax in C and C++ in this case. A function has basically 4 main components. Now, when I say main components, I do not mean the size of the component. I simply mean the meaning or the necessity of the component. The first component is a type that you specify before the rest of a function definition. This is also called the return type of a function. A return type of a function specifies where you can stick the invocation of a subroutine. So in this particular case, because subroutine f has a return type of int or integer, the invocation of f can appear anywhere where an integer is expected. Okay? So how can you use an integer in C and C++?
Boolean value.
You can use it as a Boolean value in the context of a Boolean. 0 means false and non-zero means true. Can someone name a few operators that can work on integers? Addition, subtraction, multiplication, division, mod. Okay. Comparisons. Okay. We can compare 2 integers to find out which one is larger, which one is less, or whether 2 integers are the same or not. So all of those places where you can expect an integer, we can stick an invocation of function f. That's what the return type is telling you. Okay. And you can use any return type. What about structures? The stuff that we talked about, like week before last. What about the date structure, the time structure, something like that? Can we use a structure as a return type? And the answer, surprisingly, is yes, you can. Okay. But in this class, we probably won't see a whole lot of that or any of that. But you can use any type as a return type. What about pointers? Same thing. You can return a pointer if you want to. Okay. But I'll reserve that topic until we talk about pointers further. The second component is very important because that really is the name, or we call it an identifier in C and C++. of the function. This is how you identify and say, I want to invoke that function. Okay, it's the name or the identifier. The next one is a list of parameters. In other words, in order for this subroutine to work, do we need to pass any additional information to it? And if so, how many things are we passing to it? And what are the types of the parameters? In this case, we have two parameters, x and y, and each one is an integer, and they're both passed by value or reference. They're both passed by value because we don't see an ampersand in the definition of the parameters. And then the last component of a definition of a subroutine or function is the body of the subroutine. So this is a block statement. Okay, whenever you see open curly brace, a few lines of code, and then the close curly brace, it is a block statement. So this block statement is the body of this particular subroutine. It basically says when the subroutine is called or invoked, this is what is being done. Okay. So are there any questions at this point about what I have just talked about? The return type, the name of a subroutine, parameters, and the body of a subroutine. No questions? Okay. So this is what an invocation of a subroutine looks like. In other words, we are making use of subroutine f here. We use 2 and 3 as arguments. The difference between an argument versus a parameter is an argument is used when you're invoking a subroutine. A parameter is the placeholder in the definition of a subroutine. So in this case, x and y are names of the parameters because it is seen from the perspective of the definition of a subroutine. 2 and 3 are the arguments because these are the values that we are passing to the parameters when we invoke the subroutine f. Are there any questions about the differentiation between what is considered an argument as opposed to what is considered a parameter?
So we have f initialized somewhere else though, right? So that it knows where to call it.
Sorry?
So we have f initialized somewhere else.
F is not initialized, it is the name of a subroutine.
Well, but I mean it's defined somewhere else. Right?
Yes, it is. It can be defined in the same file, it can be defined somewhere else. So that's a question about, compiling and linking. Do they have to be in the same file, or if they're not in the same file, how does the linker know where to find it? Yep.
So the type to a parameter and argument have matched, right?
Yes, that is correct. The expected type of this particular parameter is an integer. So whatever you pass to x has to be either an integer or something that can be converted to an integer automatically without you doing anything. So if you have a short integer, that's fine. Okay, if you have a short integer here, because the compiler can do certain types of conversion without having to ask you. But on the other hand, if you have a string here, like with double quotes around the two, then it's not going to be okay, because a string is an entirely different type compared to an integer. That's a good question. Anything else? Okay. No other questions? Okay. So we're moving on. How does a function work? At compile time, the definition of a subroutine or function generates a block of code inside the object file corresponding to the body of the subroutine. And the identifier of a function is used excuse me. And the identifier of a function is used as a key to locate the code. In other words, the name of a function is what we use to look up the definition. Where is the definition of a subroutine? The invocation, the calling of a subroutine causes a compiler to look for the block of code corresponding to the name of the function that is being invoked. So that means, in this case, these 6 lines of code is going to tell the compiler, hey compiler, here's the definition of subroutine f. The compiler will convert or translate this block of code into object code, and then use f as the identifier of that block of code, so that the linker knows where to find it later on if it needs to find it. On the other hand, this is the invocation or the calling of subroutine f. When the compiler sees this and it doesn't know where f is, that's not a problem. Okay, it is not a problem, because what the compiler does is to say, oh, okay, there's a call to subroutine F, and it will just defer to the linker to find out where the definition of F is.
So is it like it's kind of like scanf is already defined in the library, so it's like
Right. But in this case, you do need a prototype to let the compiler know how to properly use function F. Without the prototype, the compiler will complain and say, I don't know any function F, so it will complain and stop compiling. Right? I can give you an example. I think I have one text file here. I'm going to get rid of everything here. So in this particular case, in one file, I might have the subroutine F here. So I'm just going to redefine subroutine F here. It's a pretty easy thing to do, so I'm just going to do this. So this is one subroutine. And we can say that there's one file, really short one, and this is the entire content of that source file. Then we can have another file that has main. So here we have the other subroutine or the other source file that contains main, and it will just say if f of xy 2, 3 is greater than 4, we'll do something here. The subroutine doesn't make a whole lot of sense. It just makes a reference to the function, but that's that's what I want to illustrate. So we have two source files here. One is here, and the other one is here. The second file is going to fail when the compiler tries to process what I have highlighted here. The problem is not that F is not defined in this file. The problem is the compiler does not know what is the proper way to use F in this context. Because without anyone telling the compiler doesn't know how many parameters F is supposed to have, what is the return type of F, and so on. Okay, so it cannot make a decision of whether this really is a proper use of function F. So in the second file, in order to make the compiler not to complain about this, we need what we call a prototype of a function to tell the compiler how to make use of function F. A prototype of a function looks kind of like the first part of the definition of a subroutine, but instead of having open and close curly brace and closing the block of code, that's it. Okay, this is called a prototype of a function. In other words, what this line is really doing is telling the compiler and say that assume that somebody has function F already defined. Okay, it doesn't have to be here. Somebody else probably has it defined, but this is how you use it. Okay, it has a return type of an integer. It has two parameters, both of integer type, and the name is F. Assume it is already there somewhere. But with this information, the compiler, when it encounters this line or this part of the program, the compiler can now say, okay, I'm okay with this now. Because one, I know the return type of F is an integer, and I can certainly compare an integer to another integer, no problem. And two, I know it has two parameters, and I am passing two arguments to the parameters, 2 and 3. And on top of that, we also know the types of the parameters are both integers. 2 is an integer, 3 is an integer. The types of the argument and the parameters do match, and the compiler says, okay, I will generate the code to call function F. But then we'll say, but what about the actual location of subroutine F? It's not known to the second file. The compiler would just say, you know what, I'm going to leave a little stub here. Okay, I'll leave a little post-it in the object file to remind the linker and say, hey, linker, this call is not resolved at this point. Okay, when the linker does its job, then the linker is responsible to find out which object file contains the actual definition of the identifier F, and then resolve the linking, resolve the reference at that point. Are we doing okay so far? Understanding, how the job of a linker is different from the job of a compiler.
Not computer, but it sounds like the linker is probably more complicated.
That's actually not the case. Okay, I would certainly understand why you think that the linker has a more difficult job. But the linker only has to be able to read object files, and the format of an object file is fairly simple. It has a table of locations where you need to resolve, symbol references, and so it will tell you where is the offset of a location that you need to fix up, and which symbol it is referring to. And it will also give you a table of the definitions of that particular object file, so in case somebody else is referring to one of those labels, the linker knows how to cross-reference everything. So the job of a linker is actually somewhat simplistic, because all it needs to do is to concatenate all the object files and then resolve all the references across the files. And it doesn't need to understand any programming languages at all. Not assembly language, not C, C++, nothing. And because of that, a linker runs really fast. You can be linking a fairly large program, and most of the time it's not spent processing. It's actually spending most of its time, guess what? Doing file input-output. So because it has to read in all these object files, right? And the actual process of resolving the references is all done internal to the memory. So that can be done like quick. And then once everything is resolved, then you have to write out the executable, and that takes more time than resolving the references to each other. A compiler, on the other hand, has a much more difficult job, especially when you turn on optimization, because then the compiler has to look at your code and figure out, oh, I can see that you have variable x being defined here. It is first initialized here. It is red here, and it is also red here, and there's nothing in between that can change the value. So when you turn on optimization, the compiler has to analyze the flow of the data of each variable and then decide, okay, can I optimize this code here? Oh yeah, I can definitely do that, because this variable, once the value is set, nobody is changing it. So I can just kind of stash it in a register and not touch it, so that I can avoid having to read it multiple times. So the compiler actually has a more difficult job, and it is not uncommon with older computers that you can see when it's compiling, it will spend just a little bit of time reading from the hard drive, and then it will spend more time actually thinking about the optimization, and then it will spend a little bit more time to write out the object file. But most of the time it's actually spent thinking, compiling. And this brings up an interesting fact about the 486 processor, if I remember correctly. When the 486 processor came out, people were having problem with Linux. Yeah, what? I mean, the 486 processor is nothing special. As it turns out, the design of the 486 processor has a bottleneck. Okay, so all of the instructions has to go through one ALU. You will learn that in cisp360, but there's one component on the processor that has to funnel all the operations through. And the GCC compiler is particularly brutal when it comes to scheduling instructions. So it will overheat that component of the 486 processor to the point that it will shut down. So any attempt to recompile the Linux kernel using that particular processor requires special care. Like, you better make sure that your processor is properly cooled, because otherwise it will overheat that one single part of a processor and shut it down. It's kind of funny.
So it was written on 386. Did they change that part?
They changed the chip layout with the 486. And that has to do with how the logic gates and transistors are arranged. Yep.
We've defined a subroutine like we did at the top there. It looks like it should be perfectly understandable to the compiler, since we're saying this is subroutine F, it returns an integer, it has two integer inputs.
Right.
So why do we need this identifier?
Where?
That second, just above that. Why do we need?
Because this is the content of one file and this is the content of another file. The compiler cannot see both files at the same time. The compiler can only compile one file at a time. So when the compiler compiles this file, this is all it sees. It doesn't even know who is using function f. It just knows that, okay, here's the definition of function f, but has no idea who's using it. Now, when the compiler is compiling this particular file, it has no knowledge whatsoever of this file. when the compiler compiles this file, it is compiling it in a context where it doesn't have any assumptions other than what you include already in this particular file itself.
And so that's why the linker then is used.
That's why the linker is necessary to basically say, oh, you know what, we have a reference to f here, and it's not defined within this source file. The linker's job is to look at all of the object files, the output of the compiler, and say, oh, you know what, the object file corresponding to this source file has the definition of f. This f must be referring to the f, and it will resolve the reference so that in the executable, everything is known, and the executable won't have a problem, at runtime. Yep.
So the linker automatically looks at the other object files. It doesn't like account for the header file for that?
No. Okay, I can. Okay, from your question, I can see the necessity to kind of talk about what the header file is and how it relates to all of this stuff here. A header file is a construct used by the compiler, but it has no use whatsoever at link time. The only thing, okay, let me just give you an example here. Okay, so this line here, pound include stdio.h, is basically telling the compiler. I would call it the compiler, but it's really a step before the compiler. But I would just say it's the compiler. Okay. So what this line is doing is telling the compiler to go find a file called stdio.h, which is basically just a text file. Okay, and it will just compile the content of stdio.h as if it is a part of this program. But it is only used in the compilation process and not anywhere else. And you don't want to put this into a .h file, because if you do something like that, then if you have different object files, pound including the same header file, then you will have f defined in multiple places, and then the linker will complain about it and say, okay, you have multiple definitions of f, and that's not going to be a good thing to do. Yep.
So it takes like the entire library from that header file, puts it into the program, so that way when the linker goes back, it's already looking from within, right?
Not exactly.
But you know what I was saying.
With the header file?
Yeah, because if we're including the header file and it's being compiled, isn't then everything from that header file being put into the program, and then
Yes.
the linker's going back and going, oh, here's where f is. And then,
But it doesn't have anything to do with the linker. Okay.
I understand. No, okay.
Let me give you an example. Those are all very good questions here, so I'm going to address this before we move on. So let's start up code blocks. Because I'm using Windows today, so I don't have any primitive tool that I can use. I like primitive tools. Okay, so we're going to start a new project. So we'll go ahead and define a project, and it's a console application. It doesn't even the program itself is not going to do anything particularly useful here. Okay, so we'll go ahead and say C++. Project title is multi-file project, because it's going to have multiple source files. Sorry? Oh, folder to create project in. I think by default it picks a place for me. No? Okay, so we'll go ahead and stick it here. Oh wait, I see. Resulting file. Otherwise, it complains it's invalid. Okay, gotcha. GCC compiler is correct. Okay. Okay, all of those options are good. Okay, so now we have a sample project. So within a project, I can have multiple source files. So I can use file and say new file, and it's going to be a C++ source file. Now this is already a pretty good place to kind of take a little pause here, because you can see that when you add a file to a project, you have a choice to add a header file or a source file. The difference is a source file can quote unquote stand alone. Okay, it is actually useful. A header file is useless by itself. Okay, it is intended to be included by a source file. So we'll go ahead and create a source file first, and okay, it's a C++ source file. We'll add it to both that, and we'll put it in the same place. Okay, so we go to here. There we go. Okay.
You get to double click on main CPP.
File name with full path. Okay, so it has to be a different name. So I'll call this, f.cpp. There we go. All right, so now the project has two source files because under sources, I wish there's a way to make this bigger. Let's see, can we make it look bigger? No, it doesn't look like it. Full screen would use up the entire screen, but it's not going to make the text any larger, which is what I want to do. See, that's not really helping. Let's look under settings. Under editor, I can make the editor itself use a larger font. That's probably possible. Choose the font to be something larger, let's say 14. But that's not my problem. My problem is we can't really see the interface itself. Okay, but I can just kind of spell out this is f.cpp and this is main.cpp. So what I'll do is in f.cpp, I'm going to define the function f, just like the one that we were dealing with. So it's an integer, it returns an integer f, it's a subroutine, it has two parameters, integer x and integer y. And in the body, I'm not used to it, we just return x plus y. Okay, so that's the, go ahead.
Did you need the semicolon on line 1? Because I think on that.
This one here?
Yeah.
No, we don't.
Okay.
Because this is a definition of a subroutine. So in place of a semicolon, we put a block statement to basically say, this is what function f is going to do.
Oh, okay, wait. I thought we were in the main file. Sorry.
Oh, no.
Because the main file, when you can
Right. That is exactly it. Yep. So in main, then we have to do that. Because in main, let's say we want to find out what is the result of f of 2 and 3. Then we have a, okay, so I'm going to compile the program the way it is, and so that you can see what problem the compiler is having, with the program the way it is. Because to us, it makes sense already, okay? I have one file that defines function f. I have another file to refer to f. So what else does the compiler need? So we'll go ahead and build the program. I'm not going to run the program. It's not really that interesting. But it does say one thing here. I'll read it out because it's hard to see it. It says, error, f was not declared in this scope. It's referring to this f here. And that's because the compiler, when it compiles, it does so without looking at other source files. That is the problem. Okay. So one way to fix the problem is to say, okay, we'll go ahead and use a prototype. So a prototype of f, like in this one, is almost the same thing as an extern with a global variable. It is basically saying, assume that somebody has f defined, and f is defined to have a return type of integer. It's defined to have two integer parameters, and now the compiler is happy about it because when the compiler gets to line 9, then it knows how to deal with f. Okay, it knows that this is the proper use of f, and it also knows that we're supposed to print an integer because the return type of f is an integer. Is that okay? All right. So we'll go ahead and build again. This time, it will confirm that the program builds correctly. Okay. So no problem. The program compiled just fine. It linked also just fine without any problem. Now let me go do something that is really stupid, but the compiler won't catch it. Yep.
So when we use that prototype, it knows to look in other source files for f.
No, the linker does.
The linker does do that.
Now, but this is the dangerous part of it. The linker does not understand how many parameters f is supposed to have. It does not understand what is the return type of f either. The linker is pretty much a dumb engine that only understands this is a symbolic name f. Okay, this is a program. This is where f is referred to, and this is the definition of f. That's all it can do, is to resolve references to f as an address. But the linker is not aware of the interface of f. In other words, it doesn't know what is the return type of f, it doesn't know what parameters are expected by f, and so on. Okay, so the program, the way it is right now, works. Okay, if I run the program, okay, so when we run the program, it prints 5 right here. I know it's pretty hard to read, so it prints 5, which is the right output of the program. Okay. So what I'll do is I'm going to do something that is really stupid, supremely stupid, but the compiler won't catch it, the linker won't catch it either. I have to shield the mic when I cough, so it doesn't pop your speaker when you connect your computer to that 500-watt speaker system. You won't see the coil flying out of your speaker and across the room. All right, so this is something that is supremely stupid, but nothing can catch it. I'm going to say, you know what? I want to pass another integer z to it. Okay, and utilize z in the return value. Okay, all right. So I just changed the interface to the function and say now it has 3 parameters instead of 2. Yep.
But since we're not adding the third integer, it's not going to know what to do, right?
Well, let's find out. Okay, this is the whole thing about this setup here. Okay, so when you look at this file all by itself, are there any problems? All by itself. By itself, there's no problem because we are just saying that there's a function f, it has 3 parameters, and the return value is the sum of all 3 parameters. Syntax are all correct. We can certainly add an integer to an integer, and the return type, which is the sum of all the integers, matches the return type of the function itself. Not a problem. When you look at f.cpp, is there a problem here?
Technically, no.
Technically, no. Very good.
Because you don't know what f actually looks like. So it looks
Exactly.
like it has 2 parameters and we're passing 2 parameters.
Exactly. Because from the compiler's perspective, it is compiling this file all by itself without any knowledge of f.cpp, where the definition really is. Okay. Now, how about from the perspective of the linker? The linker says no problem, right? Because the link, as far as the linker is concerned, is that main CPP has an unresolved reference to the symbolic name of f. F.cpp, on the other hand, defines the label f. Okay, one has a reference to f, one has the definition of f. Okay, I'll connect those two, I'm good to go. Okay, because the linker is not aware of the number of parameters, nor the type of the parameters, nor the return type of the subroutine itself. Okay, so the question now, yes, go ahead.
What happens when you run that?
Exactly, so we'll go ahead and run it and find out. So we'll go ahead and say, let's build a project, and in fact, let's run it. Ah, it still prints 5.
Oh, I think we need to build it first, don't you?
I think, does it build all by itself already?
If you hit F9 on the keyboard, it'll build and run for you.
Oh, okay.
Or you can do it there.
Build and run. Okay, not just run. All right, so it has, undefined reference to f int int. Oh, it found a problem. Okay, that's only because this is a C++ program, not a C program. Okay, okay. So now I have just opened a new can of worm. But the can says it'll consume before end of day, so we have to deal with that can of worm first. Okay, so this time we're going to open up another console project. And this time it's just regular C. And I can explain why, what it is doing as well. Okay, Okay, so this is a C multi-file. Okay, GCC compiler. Okay, so we have a C multi-file program, which is with an extension of .c and .cpp, and we'll do the same thing here. We're just going to add a new source file. So new source file, new file, and then pick source. Okay, and make sure this is also a C project. And we'll pick the path and make that f.c instead of f.cpp. And do exactly the same thing. Now remember, the syntax of C and C++ are for the most part the same thing. Okay, so this time I'll jump right to the one that is incorrect. So we just return x plus y plus z and save the file. Go to main.cpp and then replace hello world with a %d, and then after that we specify f of 2, 3. All right, and we'll give it a wrong prototype. Okay, so we'll tell the C compiler and say, oh, you know what? F only needs 2 parameters, x and y. Like so. All right, save the files and build and run, and it gives us what? 460. Okay. All right.
You just pick a random value for z and put it in.
Yep. Because what happens, it's a little bit early to explain that in this class, but what's happening is in the subroutine f defined in f.c, this is basically telling the subroutine f and say, assume there are 3 parameters. Now, I cannot really tell you where those 3 parameters are really stored, because that will necessitate the explanation of what a stack is and all kinds of other stuff that goes along with it. But it is telling f to expect to find 3 parameters at a particular place. Okay, and so by itself there's no problem. But in main.cpp, this is telling the compiler to generate the code to only put things into the first 2 places out of the 3. Now, does that mean the 3rd place does not exist? No, the 3rd place is always there, okay? Because memory cannot be not existing, okay? So there's always something there where the 3rd parameter is supposed to be expected by subroutine f, except the call, the invocation, is not putting anything there. So if you don't put anything there, then it's just using whatever is at that place when the function or the subroutine gets control. And it just turns out to have a value of 55, because otherwise we wouldn't be getting 60 as a result. Okay? So this is telling you that in C, but not in C++, you can have problems like this. Okay? And I will go back to explain why in C++ it is not an issue. Okay, so I will explain that later. Okay, so how do we solve this problem? This is actually a very, very good discussion, because it explains why header files are so important. Okay, so what we'll do is now we'll go ahead and say, you know what? This doesn't belong here. The prototype of a function does not belong alone by itself in the source code. It belongs to a header file. Okay. All right, so that's not a big deal. So we go to File, we say New File, and then we say now we have a header file. The only reason why this is special is because in a header file you don't differentiate whether it's C or C++, and it will also give you some additional stuff. So we'll go ahead and name it. We'll call it f.h. Okay, just the header file of function f. We'll include it in the debug and release, and click finish. Okay, so this is the template that a header file is. When you use code blocks, it gives you the automatic protection of if you include the same header file multiple times, it's not going to cause a problem. Okay, so I'm going to put a prototype here, but I'll put a wrong one here. Okay, so I'm going to say int f, int x, int y, and that's it. Okay, this is the wrong prototype. Doesn't match the actual definition. Save the file. Go to f.c. And what you should do is when you have a header file for a particular function, you do it here. You include f.h here. Now, there's no problem with having a prototype, to be in the same file as the actual definition, as long as they agree. That's not an issue. It's only when they do not agree that we have an issue. Okay, and we'll do the same thing in main.c. So in main.c, I'm no longer sticking this one here all by itself. I'm basically now pound including f.h. Yep.
Where did we create the header file f.h?
Where?
Yeah.
It is not seen here because it's not a source file, but it is included by both of the source files. Are we doing okay so far with this code? Now, I still have the same error. Okay, I still have the same error of the prototype not matching the actual definition, but this time the compiler can catch it. Because I am pound including f.h in the same source file that is actually defining the subroutine. So now the compiler can say, hey, you know what? You told me in the prototype that we're only expecting 2 parameters, but when you're defining it, you're saying that it has 3 parameters. Okay, there's a problem here. The compiler will complain about it and says stop. Okay, so let's go ahead and try it. And I have to stop the debugger first, I think. The debugger is still running. Debug.
Open up your command prompt, the window, and have like your 60 in it.
Okay.
It's on your down.
Oh, right there. Okay.
Actually,
Yep.
it's the one on the far right.
This one.
Yeah. Just
Oh,
hit-
okay.
just hit
Press
a
enter key so you can exit. Thank you.
So, did
Yep.
we? Now, where did f.h come from?
F.h is just a file that I added to the project by doing an f file, new, and then file.
Okay.
Yep. Okay, but it is here. Okay, it's a part of the project, but it's listed under headers. Yeah, that's why it's not showing up in sources, because a source file is what the compiler needs to start with. It can potentially pound include a header file, so that's why the header files are kind of in its own category. It's not grouped with the sources.
And do we put anything? What did we put into f.h? I'm sorry.
That's the content, just the prototype. Okay. All right. So now let's go ahead and build the program again and see what the compiler has to say. And the compiler complains right here. Okay, let me see. It complains in f.c on line 3, conflicting types for f. Okay, let's double click it, and it places it right here, which is the proper line, because the prototype says we only have 2 integer parameters, but the actual definition disagrees and say that we have 3 integer parameters. Yep, go ahead.
This would work the same way if, say, we weren't doing all this, we had on our function declared inside the same source file, inside the main. If, like, let's say we just had f defined underneath main, but hit the prototype,
Yep.
would it also catch?
Yes. Yep.
And then, so that's
Anytime you have your prototype not agreeing with the definition, it will catch it.
as long as they're in the same, or like, other than this, like,
Yeah.
if they're in the same thing.
As long as the compiler can see both at the same time. They don't have to be in the same file, because technically the prototype is in f.h, it's not in f.c, but because of the pound include, the compiler sees both the prototype and the definition as if they're in the same file.
And then with prototyping, if we do include it inside of the main, is there a difference between putting it outside or declaring it inside of the main? It's like I did with the fixes, the extended problem, I put the prototype inside of the main and it worked fine.
Pound includes are supposed to be outside of a function.
Not about the prototype.
Or the prototype,
Yeah, so I had put like if you put them outside of the main.
that would be the same. Yeah, if you put a prototype inside a function, it simply means that the compiler will not cannot see that outside of the context of that function. Yeah.
What do you mean it can't see it outside the context of the function? What's that mean exactly?
It means okay, let's try that here. That's okay. I mean, those are all really good questions. It means that you guys are processing the information. Okay, so let's double check and make sure this one builds first. Okay, build. It's complaining. Okay, that's because I still haven't fixed my problem here. Okay, Okay, so there are two ways to fix the problem. I can just fix it here. Build again. Okay, so there's no problem here. So in main, because not that one, this one here, because I do a pound include f here. So let's check, if I define the function g here, whether g already has visibility of f. So we'll make g returns an integer, and just say return f of 2, 3 here. Because if this tells me that the prototype should be visible only within main because it's local within that block, so that means in G, this f should have a problem because the prototype should not be seeable, should not be active at this point. But that's just my understanding. I'm not sure. Yep, that's what it's complaining. Yep. So when you do a pound include inside a function, whatever is in the header file can be extern, can be prototypes and whatnot. They can only be used within that block. Outside of the block, it doesn't exist anymore. Which is the proper, way of interpreting what is a local scope. Okay, there we go. All right, so this is going to work now. Okay, we can build again, and everything works because I just fixed the definition to only have 2 parameters. All right, but we still have one mystery, don't we? Because in the C++ code, that's not what we do. Okay, in the C++ code, we have the definition being, having 3 parameters. We have the wrong, quote unquote, wrong prototype here, and make use of the wrong prototype here. And yet, the linker is really smart. Oh, okay, we have to switch the project back to this one. Target is up to date, nothing to build, all items are up to date. Okay, let's try this. Save it. Build again.
Try right clicking on one of the source files. Which one did you do? The main one? Right click on the main file. And then build file.
Yeah, the compiling part is not a problem, it's the linking part that is going to be a
I
problem.
think that I think though if you do it that way, then when you build it should be in that project now.
Right, because it's refreshing it. Okay, so the question now is, why is the linker capable of complaining that we have a problem of a undefined reference of f of 2 integers instead of saying, hey, the other one has 3, you only have 2, we have a type mismatch. This is a very interesting, issue because remember what I said, the linker does not have any idea of the types of the return type and also the types of the parameters. I did not lie, but I didn't tell you the whole truth either. Okay. It is still true, okay, what I said was actually true. It still is true that the linker has no knowledge whatsoever of types of the return type of the function itself, nor the types or the number of parameters of a subroutine. That is still true. Okay. However, okay, this is the big however that I forgot to mention, is the name, the actual name used by the linker or visible to the linker in C++ is what we call a mangled name. Okay? It has what we call a name mangling ability. What that means is the actual name seen by the linker as far as the reference to f is concerned here, and as well as the definition of f here, that is not just f. Okay? It is actually going to be a longer name that actually has the type of the return type as well as the type of the parameters as a part of that mangled name. So, okay. It's called mangled because it gives you the pretense of f is just the name of the subroutine, but in reality, as far as the linker is concerned, the actual name of this subroutine is not f. It is something that is really long and gibberish that we don't want to deal with, but since the compiler and the linker can deal with really long and complex names. So that's why it's called name mangling. Yep.
So you're basically saying that the linker sees all of line 1 as the name instead of just the letter F.
More or less, yes. More or less. It's using the return type as well as the types of every parameter as a part of the name. So what you said is basically the truth. But to the linker, it is still just the name. Okay, it's not really aware of the actual type. It is just the name.
So when we give the prototype, the compiler creates a name that's basically doesn't match up with.
Correct. Yep, that's what happens. And that's why this complaint is coming from the linker and not the compiler. Because the linker is looking up a name that implies there are 2 parameters, but it can only find a name that implies there are 3 parameters, so it's not matching up.
If you had, I don't know why you would do this, but let's say you had 2 definitions of F.
Oh, you can do that.
And one that has 2 and
Yep.
one that has 3. Would it pull the right one then?
Yes, it would. Why? Because we can.
And you still call them both F?
Absolutely.
That sounds like a terrible.
No, it's not. Well, this is actually, okay, now you might think this is not a good idea because you can seem to be able to introduce problems, but this is how C in and C out works. Remember, when we use C in, we were using the same right shift operator, greater than, to read in an integer, and using the same thing to read in a character. Remember that? So how can that work, right? Because the mechanism of reading in an integer is different from the mechanism of reading in just a character. So it has to go to two different places, right? The logic is different. So how can that be the same operator? It's because the type of what you're reading in is actually making that particular operator specific to that type. So when you specify a character, reading into a character, it knows, hey, we need to use that subroutine to read a character. But when you specify we are reading in an integer or a float or something else, it knows where to go or which subroutine to actually utilize in order to finish the operation. So this will work. Okay, so let's go ahead and save this file, build all, and you can see the compiler does not complain at all. And when you run the program, it will run just fine. It gives you 5, the correct answer.
Is it similar to structure?
No, it is related, but it's not the same. We call this, I'll answer your question, I just need to find it. It's called, it's right at the tip of my tongue here. It is called, okay, I might find that in my own outline of the class. Okay, let's answer your question first before I forget that.
Well, I was just saying, if using the same name F, you're allowing yourself different numbers of parameters to be entered. So, like, you get 3 parameters once to go to that other F, it gets 2 parameters. So that way, it kind of basically doesn't pull a random value out if C isn't given.
Correct. Yes, but the 2 functions are completely independent from each other. One can return a sum, the other one can return a product, and no rule says they can be, they can be very different from each other. They don't have to be related at all. Let me go look up the course outline, because in the course outline I probably have that listed under functions. So excuse my scrolling. Structures, libraries, and okay, it's called function overloading. That's it. We are using the same name of a function, but because we change any one of those things, okay, the return type or the types and the number of parameters, it is called overloading because we are using the same name, but it has different interfaces to the same subroutine. And that's a C++ only feature, as we have just demonstrated, because the C compiler was not able to catch it at all, but yet the C++ compiler was able to catch it. But that's only because of what we call name mangling. which is a real term. Okay, some of you think that I just made up the term, but if you look up C++ name mangling, it's a real term. Now it is a long article. I'm not going to ask you to read through the entire thing, nor am I going to read the entire thing to you. But it has to do with, I do want to explain it because it's a part of the history of C versus C++. And at some point of time, you will run into this type of thing too. So the reason why we have name mangling has to do with when Strustrup, the person who wrote and invented the C++, the programming language, when he first developing C++, he did not want to write his own compiler. Because writing a compiler is a major undertaking, and you don't want to do it, when you're just, researching and doing something. So what he did instead is he made C++ a somewhat of a preprocessor on top of C. In other words, okay, we have a translator on top of a translator here. Okay, think of object code as Japanese, think of C as English, and then think of C++ as Spanish. Okay? Strustrup says, I can easily translate into English, but I don't want to learn a whole different language that is like Japanese. Okay? But unfortunately, the processor can only understand Japanese, right? So what do? Then you say, hey, you know what? I know someone who can translate from English into Japanese. So all I need to do is to translate Spanish into English. That's C++. C++ is Spanish. C is English, and then object code is Japanese. So Strustrup basically took the shortcut. And that's how name mangling came along. Because he can no longer, because of function overloading, he cannot use just F to represent the name of a subroutine anymore. He has to make use of the types of the return type and the types of the parameters to make up a part of the name, and that's where name mangling came from. Okay. Now, if he started off writing C++ as a complete compiler and not as a level or a layer on top of GCC or the C compiler, then there would not have been any type of name mangling at all. So so there you have it. The kind of the long history of why we have name mangling. But I think the most important part of this little experiment is to show you one of the subtle but yet important differences between C and C++. They just look at things differently. Sometimes when things seem to be about the same, they are actually being seen differently by the two compilers. All right, so this is actually a pretty good discussion. I like it. All right, so we are back to function. There we go. All right, so getting back to the function here. At runtime, the definition of a subroutine does not do a single thing by itself. Okay, so it's kind of like having a function is like a page in a spell book. Okay, I know some people may not like to talk about witchery and stuff like that, but that's what I'm going to do anyway. So it's like a page on a spell book. Okay, does it do anything? No. Somebody actually has to read and cast a spell, to invoke a spell, to do something, right? That's the invocation. The invocation of a function, the invocation of a spell, same thing. Okay, so until you make use of that knowledge on a P on a book, it remains just as text. It doesn't do a single thing. Sorry?
Light as a Feather still supported from a movie.
Oh. But talking about movies, the next time we meet is going to be on the 26th, and the Friday is the 28th. And I know many of you are thinking, Black Friday, got to go to Best Buy or some other places, right? Well, I just want you, as you go shopping, okay, if there's a theater next to the shopping mall, check out the movie called The Imitation Game.
Alan
Alan Turing It's based on the story of Alan Turing, except they twist a little bit of the original story and the character. But from what I was reading, it was a fairly good representation of what happened. And I know we are not supposed to talk about movies, but I am supposed to talk about stuff that is related to computers and programming, and it cannot get any better than this, okay, from that perspective. It's called the Imitation Game. Sorry? Trailer?
It's up on the videos tab, and you'll see it.
There's some trailers. I don't think the trailers are very...
I think it's Benedict Cumberbatch is the lead guy.
Yeah, he is.
The villain from the last Star Trek.
Okay, there we go.
This war, we're not winning it. If you speak a word of what I'm about to show you, you will be executed for high treason. It's beautiful. It's the greatest encryption device in history, and the Germans use it for all communications. Everyone thinks Enigma is unbreakable. Let me try, and we'll know for sure. Mr. Turing, do you know how many died because of it? I don't. 3. While we've been having this conversation. Gentlemen, meet Mr. Turing. We to work together then. I'm afraid these men would only slow me down. Popular at school, way.
We're short on staff.
We get more staff then.
You have 6 minutes to complete the task.
It's impossible. No, it takes me 8. 5 minutes and 34 seconds.
You said to do it in under 6. What is it that we're really doing?
We're going to break an unbreakable Nazi code and win the war.
You have to pull off this irascible genius routine. One actually has to be a genius.
I'm designing a machine that will allow us to break every message, every day, instantly.
You're going to need all the help you can get, and they are not going to help you if they do not like you.
Have you decrypted a single German message?
You will never understand the importance of what I am creating here.
Our patience has expired.
No!
If you fire Alan, well then you'll have to fire me.
Me too. And me.
That's a bloody word.
Alan, you do not have to do this alone.
What are you doing? What's going on?
Navy thinks one of us is a Soviet spy.
You've got more secrets than the best of them. What if I don't fancy putting it that way?
Can't tell anyone home. It's illegal.
I'm just a mathematician.
Sometimes it is people who no one imagines anything of, who do the things that no one can imagine.
Look good.
Yeah, there's 50 shades.
We talked about that. They got
You did? Okay. Now, the interesting part about this is there are a few really key events in the history of computer science to get us to where we are at this point. This is somewhat ground zero. This is basically what started the whole thing. Was the Germans were using what they call the Enigma encryption machine, which looks like a typewriter, to encrypt messages. In other words, the signal is broadcast. Okay, everybody can capture the signal itself, but because the signal itself is all the actual message, the content is encrypted, you are just going to get gibberish. Okay, your characters out of order, random gibberish, that you cannot understand. But they found they understood the importance of being able to decrypt messages from the enemies, and all military people know that. But the British, found that there are somewhat irregularity in some of the transmissions, and they were exploiting that. Okay, these were the original hackers. Okay, these were the original hackers because they did it by hand originally. So I think it was the Air Force, the German Air Force did not really follow the procedure of making sure the encryption is unbreakable, because the encryption scheme itself is not the flaw. It is how they use the encryption machine that was flawed. Okay, because they open up each message with the same letters, okay, with the same letters every single time, and they use the same encryption configuration every single day, okay. So the Brits eventually found out, hey, there's some regularity here. We can break this, and they did. They broke the code. And this movie was aired in Britain on the 14th instead of the 28th because it is in memory of the Blitz. Okay, the German basically flung, is it the V2s and V1s, you know, or the bombers? Anyway, by that time they already had decrypted messages from the German, doing it by hand, and they knew it was coming, but they could not let people know and evacuate, because if they did, then the Germans would know that their code had been broken already. So that's why in the Great Britain it was aired. The movie was aired on the 14th, debut on the 14th instead of the 28th here.
So they just let their own citizens get bombed because
Yeah.
they didn't want the Germans to know.
Yeah, pretty much. They had to pretend that they did not know about it. It's a hard decision because you're trading off people who would die in the Blitz as opposed to possibly many more people that you can save later on in the war and actually winning the war as a result. So it's definitely a hard decision, and the movie actually represented that part as well, and also the personal history of of Turing, which had issues. At least back in those times, there were issues, like social issues that still exist, to a certain extent today, but not nearly as much. You guys have to watch it to find out, what it is and how the movie ends. Okay, but getting back to the landmarks of computer science. This was the first one, okay, of modern computers. This is the application. They were doing it by hand. It was basically a mathematical problem to begin with. And Alan Turing is not an engineer. He's not a mechanical engineer. He's not a machinist. He's a mathematician. So he figured out a way to systematically break the code, and it was done by hand originally. But at the end of the war, the German added one more disk to the Enigma machine, which basically made it intractable for humans to break the code. In other words, it is still breakable. It's just that by the time you break the code, it's useless. Because whatever they were planning, they were say that communication set will be bombing that place. By the time you decode, it's going to be 2 days after. So the information became useless, even though it was still doable. And that's when they switched to a mechanical/electrical computer to automate the process. But it's based on the same theory of decoding the code to begin with. So when you go to a 4-year university, you will probably have to take a class called computational theory, or some schools call it automata, automata, automata. And that's Alan Turing's work, okay, original from the 50s. Okay, and the way he models the operation of a computer as a machine is still valid today. So that's the first landmark of modern day computer science. At that time, computers are hardwired. In other words, if you want to change how a program operates, you have to open up the computer and change the wiring inside, or maybe even mechanical parts. Okay. And so, how do we get to the computers today, where or cell phones, where you can just kind of download a new program and it will run the new program instead of having to open up the computer and do all the rewiring? So the second major person who contributed to computer science is John von Neumann. Okay, and some of you may have heard of the term von Neumann architecture. That's the guy who came up with the idea of let's not hardwire instructions or how a program operates. Let's store that information the same way we store data, numbers, things to be processed, so that that can be changed pretty much on the fly and say, oh, you know what, I don't like to run this program anymore. Let's load another program into memory and run the other program. So that's John von Neumann who made that contribution. So in many ways, that movie, even though it has nothing to do with C and C++ programming, But I think in many ways it is inspiring because it really connects us back to how computer science began as a necessity. It was not something that's fancy. It's not like games or anything like that. It was a necessity to win a war, or to the British not to lose a war. So I know I'm using a precious time today to do this, but sometimes I think that's actually important too. So we are kind of here. So I want you guys to kind of read about this. We talked about this already. Okay, this is not the first time we talked about it. We have talked about it already. And then from here we'll move on to top-down design. With top-down design, we still have about a minute or so. So I'm going to use up 1 minute of your time. This won't take long, and it's not going to be very boring either. Top-down design is about, let's go all the way out. It's about finding Hong Kong on this map here. Okay. Now, first of all, a few things to notice. If you just combine all of the text, I know you cannot read everything because it's kind of small, but if you just combine all of the text, all the labels here, how many labels do you think are there here on this map here?
Just the text?
Yeah, just the text, yeah. 50, 35, so that'll be the order of magnitude, okay? I don't need the exact number, okay? So it'll be in multiple teens, okay? That's looking for a particular name within tens of something. Would that be exceedingly difficult, or is it kind of doable? It's doable, okay? So what if I tell you Hong Kong is a part of China? Can you locate China? Even if let's say you're a Martian, you have no idea what is China, I just tell you how it spells, it still would be possible, right, to locate, China, C-H-I-N-A, on this map, okay? So here's China. Let's zoom in. And can you find Hong Kong at this point as a label? And how many labels do we see here, on this particular level of a map? Oh, it would still be about 30, 40-ish. Okay, I don't think there's any more, in this map here. Okay, so let's say I'm looking for the Cosmopolitan Hotel in Hong Kong. Okay, a particular hotel in Hong Kong. Okay, so we know where Hong Kong is now. So we can now pretty much zoom into a more or less local map of Hong Kong. Okay, all right, so this is a local map of Hong Kong. And since you guys may not know, where places are in Hong Kong, I can tell you that that hotel is on Hong Kong Island. So do we know where to zoom in at this point? Is there a label saying this is Hong Kong Island? Okay, well, it's kind of right here. And once again, you can see that at this level, there are about 20, 30 names or so on the map. Okay, which means going through each and every single name is doable. Okay, it's not very difficult. Okay, so here's Hong Kong Island, and I'm going to zoom into Hong Kong Island. And what if I tell you the hotel is somewhere around Happy Valley? Okay, you guys can find Happy Valley. Okay, that center exactly. Yep. So now we zoom into Happy Valley, and there we go. What if I tell you the hotel is next to Queen Elizabeth Stadium? Not that the Queen actually doesn't a whole lot of exercise, but it's named after her anyway.
Yeah.
All right. Okay, what is common here? Okay, what do you think I'm trying to illustrate here?
Each file contains several other files, like each name contains several other names.
And each level does not give you exactly, it doesn't give you like 200 items on the screen that you have to search through. Each level gives you a certain number of things that you have to look through, but it's manageable. Okay, so that's really what top-down design is about. It's basically controlling the complexity at each level to a point where you can look at each level and say, I can do this. Okay, mentally I can track all of these things. Now, obviously, we're not going to deal with road names or parks and stuff like that in programming, but we are going to deal with what? Variable names, structure names. We're going to deal with subroutine names. We're going to deal with loops, conditional statements, and so on and so forth. So basically, at each level, we're saying, okay, we're not going to write a single function that is 500 lines long. Okay, we'll limit it to about 50, 60 lines or so. It would be nice if we can offer it in one page, like physical page, because this way, you don't have to page up and page down just to find the beginning or the end of a construct. That is top-down design, the philosophy of top-down design. Okay, does that make sense? Okay, so we'll stop here, and then on Wednesday, what we'll do, I'll give you a little preview, and some of you can remind me to talk about it because I may forget that that's what I'm going to talk about. Okay, I have a problem with this statement here. Using top-down development in the implementation of functions. I have a problem with it. Okay? This statement seems to imply, maybe it's just my understanding of the statement, but this statement seems to imply that top-down is the right way to implement functions. Is that what you understand too from this statement? Okay? And I have a problem with that. Okay? So on Wednesday, we'll talk about why I have a problem with that and what people actually do in practice. Okay? All right. So I'll see you guys on Wednesday, which will also be the time when we talk about the exam.
Also, we're reviewing the exam on Wednesday. We're going to go over the exam answers on Wednesday.
Yes.
Are you handing them back Wednesday?
Yep.
They won't be graded.
It will be completely graded.